Welcome to Module 24, Scheduling, Occupancy, and Optimal Start-Stop. In this module, we treat the schedule as an operating contract. It must represent how the building is actually used, who can change it, what exceptions are allowed, and how the HVAC system transitions into and out of service. A good schedule saves energy without creating comfort, humidity, ventilation, or recovery failures. The objectives are practical. Learners should be able to design schedule hierarchies, coordinate operating modes, handle temporary occupancy and holidays, explain optimal start and stop, avoid conflicting schedules, and verify actual recovery. The goal is not only to make equipment turn on and off. The goal is to make time-based control reliable, visible, and testable. The core concept is that scheduling is an operating contract. It expresses how the space is used, what exceptions exist, and what the system must protect during transition. A technically perfect sequence wastes energy if it runs continuously, but an aggressive setback can also create comfort, humidity, or process problems if the building cannot recover. A good hierarchy may include enterprise calendar, building schedule, area schedule, equipment schedule, and approved local exceptions. The hierarchy is not the same for every site, but ownership must be clear. If both the server and the controller own the same schedule without a defined relationship, the building can run unexpectedly or fail to run when needed. Schedules select operating modes. Occupied mode may require comfort and ventilation. Standby may use wider set points and reduced airflow. Unoccupied may use setback and protection. Warm-up and cool-down prepare the space. Purge may be a defined ventilation action. Emergency mode must follow approved high-priority requirements. The sequence should not rely on one on-off schedule when the system really needs explicit modes and transitions. Temporary occupancy is useful, but it must be controlled. A local push-button room reservation or operator request should condition only the necessary area and its support systems. Every exception needs duration, expiration source, and an audit trail. A temporary override without expiration becomes a permanent energy problem. Calendar governance includes holidays, daylight saving changes, time synchronization, local time zones, and change approval. These may seem administrative, but they create real failures. A wrong holiday can leave a building unconditioned or running all day. Clock drift can break local schedules. The design should define what local controllers do if the enterprise schedule is unavailable. Optimal start estimates how early equipment must begin so conditions reach target by occupancy. Inputs may include indoor temperature, outdoor temperature, historical recovery rate, plant availability, and day type. A robust algorithm has minimum and maximum bounds and learns only from valid recovery. If yesterday had a valve fault or open window, that period should not become normal learning data. Here is the example from the chapter. A zone is 6 degrees below occupied heating set point at 5 AFM. Valid historical data show recovery of 2 degrees per hour under similar outdoor conditions. The starting estimate is 3 hours, but the algorithm must apply minimum and maximum bounds, verify plant availability, and reject invalid learning periods. Optimal stop may reduce conditioning before scheduled vacancy while the building remains within acceptable limits. It is not appropriate where process control, humidity, or critical occupancy requires full control until the end. The sequence should monitor representative zones, outdoor conditions, and building thermal behavior. Fixed early, stop without feedback is simply a schedule change. Schedule conflicts and fallback must be designed. If enterprise and local schedules disagree, the active owner and source should be visible. Temporary occupancy should expire. If the enterprise schedule is lost, local controllers need bounded fallback behavior. Abrupt time corrections should not cause unsafe cycling. Operators need to see the active schedule source, active mode, next transition, and fallback status. Verification requires trends, include active schedule source, operating mode, temperature, humidity, fan requests, plant requests, ventilation state, recovery start time, achieve time, alarms, and overrides. The goal is to prove the transition. Did the building reach target by occupancy? Did it preserve ventilation and critical limits? Did an override or equipment fault distort the learning data? Common mistakes include duplicate schedules, treating unoccupied as complete shutdown, allowing temporary occupancy without expiration, starting more systems than needed, and calling fixed early start optimal start. Other failures include learning from invalid recovery periods, ignoring time zone behavior, and having no local fallback. Let us summarize. Control time with ownership, modes, limits, feedback, and recovery. A schedule is an operating contract based on real occupancy. Hierarchy and ownership prevent conflicts. Temporary occupancy must be visible, proportional, and expiring. Optimal start and stop require valid recovery evidence and bounds. Calendar, time synchronization, and fallback behavior must be tested.